Так, вот сегодня у нас выступает Олег Юрьевич Арестов из Арбина, и название доклада «Алгебры аналитических функционалов и гомологические эпиморфизмы». Today our speaker is Oleg Aristov from Harbin Institute of Technology, and the title of his talk is Algebras of Analytic Functionals and Homological Epimorphisms. Please.
First of all, I'm grateful to the organizers to the possibility to speak again at this seminar at the main seminar in my life, I suppose. Yes, I will speak about analytic functionals and homological epimorphism. Wait a minute. So, but in fact, this talk is a continuation of talks given 7 years ago, no, as well as previous talk in the spring. So, main theorem was announced 7 years ago, but only this year I have got a complete proof that for each connected complex Lie group, the Arens-Michael envelope of the algebra analytic functionals is a homological epimorphism. And as a step, we use a small generalization of the result, which also, I told about this result a half a year, also old, announced 7 years ago, but complete proof was obtained only last year that for a solvable complex Lie algebra, the arithmetic envelope of its universal mapping algebra is a homological epimorphism. And in both theorems, I use relative homological theorem. And in fact, the proof is rather technical, and it consists of 4 main steps. The first step is a reduction to the case of Stein group, next to the case of linear group, next to the case of simply connected solvable group, and finally the proof in the case of simply connected solvable group. And so I begin with some comments. So if we have two topological algebras, A and B, of course, topological algebras with locally convex algebras with jointly continuous multiplication. So if we knew something on homological properties of A and B, then we can say something about its properties of its tensor product, projective tensor product. But when we work with algebras of analytic functionals, we must use analytic smash product. A smash H, for example, when we have some action of a topological Hopf algebra, H on the algebra A. Then knowing the properties of A and H is not sufficient. We need to know something about interaction between them. And so we need topological properties of smash product relative to A. And so I recall the definitions. The algebra of analytic functionals. If we have a complex Lie group and the space O of G of holomorphic functions on G, of course with the topology of uniform convergence on compact subsets, then algebra of analytic functionals A of G is a strong dual space of O of G, and endowed with the convolution multiplication. A of G is similar to the algebra of distributions in the case of a real Lie group. And it can be treated as an analytical analog of the universal enveloping algebra of Lie algebra. And also A of G gives homomorphic representation of G in a locally convex spaces. One simplest example is, of course, analytic functionals on complex plane C. In this case, we are Fourier transform. We have an isomorphism with the algebra of holomorphic functions on exponential type. And now Arens make envelopes. Most topological algebras in functional analysis are C-star algebras, Banach algebras, or some algebras approximated by them. Standard examples: algebras of operators, differentiable functions, holomorphic functions, all they are Arens-Mike algebras, but its projective limits of Banach algebras. Or equivalently, the topology is determined by a family of submultiplicative seminops. But of course, there are exceptions. Exceptions are algebras of distributions, our analytic functionals, our main example, and also algebras endowed with the strongest locally convex topology. And it was an idea of Joseph Taylor, 50 years old. Idea was to find an Arens-Michael algebra closest to a given topological algebra. The completion of given algebra with respect to all continuous submultiplicative seminoms is called the Arens-Mike envelope of A. It's in this Arens-Mike envelope is algebra closest Arens-Mike algebra to a given algebra A. The main example is Arens-Mike envelope of the algebra of polynomials. And then we get the algebra of entire functions and variables. In fact, this is a simple exercise. And third main notion today, homological epimorphism. They are also introduced by Joseph Taylor many years ago, and this idea later appeared in pure algebra. Flat homomorphism from A to B, that means that B is a flat A model, is a standard concept in algebraic geometry. And I suppose maybe this example, so the idea of a flat model gives from examples from algebraic geometry. But for new non-commutative rings, flatness is too strong property. And also it's too strong property for topological algebras. For example, the homomorphisms from the algebra of entire functions to the algebra on the disk is not flat in topological homology. It was noted Krikowski maybe 25 years ago or something like this. But nevertheless, it is homological epimorphism. So homological epimorphism is a weaker notion and a good replacement for flat homomorphisms. Homological epimorphism has many names: absolute localization, lifting, stably flat homomorphism, isocohomological morphism, homotopia epimorphism, and so on. Now, I recall some notions from homological theory. We used complete projective tensor product of locally convex spaces, and we write the sign of tensor product with algebra and model, but this means complete, and the multiplication is factors through the tensor product, or equivalently is jointly continuous. And for example, each associative algebra of countable dimension is such an algebra with respect to the strongest locally convex topology. All morphisms are continuous, and of course, the definition of projective model is standard. A model P over A is projective if for every morphism of model from X to P that has right inverse continuous linear map, then there exists a right inverse model morphism. And projective resolution of a model is a complex that splits by continuous linear maps, and all members, except M, of course, are projective. And from the general point of view, we can use the exact category where admissible complexes are those that split by continuous linear maps. We also use the projective tensor product of A models, M and N, at the denoted on both the side. And so the definition of homological epimorphism. We have a homomorphism, of course, continuous. The first property, but it is a epimorphism, but can be right as a equivalent definition that the natural map from B times B over A to B is a topological isomorphism. And second property is that it is homological. So we take arbitrary projective resolution of A in the categories of topological A by models. Then we applied the factor of tensor product over A by B from the left and from the right at the same time. And then we get this sequence, and if the sequence splits by continuous linear maps, so admissible, then we say that we have homological epimorphism. Well, for example, we take the algebra of homomorphic functions of exponential type and write the resolution, the method resolution. In fact, this is a Cauchy resolution in dimension 1. Here, pi is a restriction on the diagonal, and delta 0 is given by multiplying on the z1 minus z2. And this sequence splits by map z to z1. And then applying the tensor of the factor of tensor product, we have a similar sequence, but with the algebra of entire functions. And this sequence also split, all formulas are the same. This means that the embedding of OXC to O of C is a homological epimorphism. I recall that the OX of C is isomorphic to A of C, the algebra of analytic functionals. And moreover, Akbarov proved that the arithmetic envelope of the algebra of homomorphic functions of exponential type is the algebra of all entire functions. So we have an answer for the general question in the simplest case. And the general question is, if we have a topological algebra, when the homomorphism of enveloping homomorphisms from A to arithmetic envelope is a homological epimorphism. This question is not easy in general because I don't know cases where we can prove that the answer is yes or no without explicit description of the envelope. So we don't know how to study this question without this description. But this explicit description is sometimes not easy. Taylor studied this question. He gives first examples, counterexamples. For example, for the algebra of polynomials, the answer is yes. He naturally came to the case of the universal envelope of a finite dimensional complex Lie algebra. Oh, this slide about Lie algebra case, not about Lie group. For a finite dimensional complex Lie algebra, the question was when the Arens envelope of the universal development algebra U of G is homological epimorphism. First results was obtained by Taylor. If G is abelian, the answer is yes. If G is semi-simple, the answer is no. And after 30 years, appeared new results. No, in fact, when I was young, I think that the most difficult case in Lie algebra theory is semi-simple case. But in fact, the nilpotent case is most difficult because there is no general theory. There are some partial theories and some partial cases, but no there some general theory. No, nevertheless, first was proved the answer yes, that if G is metabelian, the result was obtained by Dorsey. Then for positively graded, the answer yes, it was proved by Perkowski. Later, it was proved for nilpotent algebras with normal growth. And finally, I'll answer yes for all nilpotent Lie algebras. And no, and after this, the last step was to understand the solvable case. And the answer is that this map is a homological epimorphism if and only if G is solvable. The necessity was proved by Perkowski, and its efficiency was proved last year. And now about the Lie group case. First, if we take a simply connected Lie group G with Lie algebra G, small, then the Arens envelopes of A of G and U of G small are isomorphic. And moreover, the natural embedding of U of G to A of G is a homological epimorphism if and only if G is solvable. This is the result of Perkowski. So in fact, the question about the envelope of U of G is a partial case of the question about A of G. And if we compare two cases, we know that for Lie algebras, the envelope is a homological epimorphism if and only if G is solvable. For a Lie group, we don't need this assumption of solvability. The Arens envelope is a homological epimorphism for every connected Lie group G. This is our main result. And in fact, the second theorem reduces to a variant of that efficiency in the first theorem. So first step of the proof, reduction to Stein groups. No, this is simple step. First step from 4 steps. I recall that Stein manifold is a complex manifold having sufficiently many holomorphic functions. And every connected Lie group contains a smallest closed normal subgroup such the quotient is a Stein group. This is a very old result of Morimoto. And from this, we very easily to derive that the map from A of G to A of G over M is an isomorphism. So we, instead of initial algebra A of G, we can consider the algebra on G over M, which is a Stein group. So we have a reduction to the Stein group case. Step 1, a little more complicated, the reduction to linear groups. If we take a closed normal subgroup of a connected Stein group, and if n is linearly complex reductive, this means that n is a universal complexification of a compact Riemann group. And from this, we have that A of n is homologically trivial. This means that it has homological bidimension 0. So the most strong property for homological property for topological algebra. And from this, we have that A of G over n is projective as left AG model. And from this, we have that each projective resolution in the over category of AG over n models is a projective resolution in the initial category of A of G models. And this argument we apply to the linearizer, that is the intersection of the kernels of all finite-dimensional holomorphic representation. Moreover, the linearizer coincides with the intersection of kernels of all homomorphisms to groups of invertibles of Banach algebras, not only to finite dimensional Banach algebra, but all Banach algebras. And from this, we have that the envelope of A of G is isomorphic to the envelope of A of G over lambda, where lambda is the linearizer. And moreover, the linearizer is isomorphic to a power of complexification. In fact, it's a complexificated torus. In particular, it is linearly complex reductive. Note that these two results on linearizer were not proved by experts in Lie groups, and so I had to do it myself because I'm not an expert, but I really needed the results. So from this we have the proposition that if homomorphism prop A of G over lambda to its envelope is homological, then the homomorphism from A of G to this envelope is homological. But two envelopes coincide, and so it suffices to consider the quotient over lambda, but the quotient over lambda always linear. So we get a linear group, and we made a reduction to the case of a linear group. Step 3. This step is more complicated. First, we need classical result, a result of Hochschild. But if we have a connected complex linear group G, then it can be represented as a semi-direct product of simply connected solvable group and linear complex reductive. And our next purpose is to reduce it to B, as to in this case, the algebra A of G has a decomposition into an analytic smash product. Here, topological Hopf algebra A of L acts on the algebra A of B. But before, we need to know how to complete A of G to a Banach algebra. And here we need Akbarov's construction. Some multiplicative weight on a locally compact group, not only on Lie groups. is a locally bounded function that satisfies to standard subjective inequality. And if in addition G is a complex Lie group, then we take the Minkowski functional of the closure of the absolutely convex hull of delta functions, so the values at a point known by the value of the weight omega. And we get a seminorm, and the completion with respect to this seminorm is a Banach algebra. This is a result of Akbarov. We can compare weights up to a power and get an order relation. For each complex generator, locally compact group, there is maximal equivalence class of weights. And for connected Lie groups, this maximal class is a class of the weight associated with the left invariant Riemannian metric. Further, if we have a weight omega, then every its power is also some multiplicative weight. And then we take the projective limit of Banach algebras A omega n of G, and this algebra is a Arens-Michael algebra. And Akbarov proved that if initial group G is compactly generated, for example, connected, then the envelope is isomorphic to this projective limit, A omega infinity of G, for every maximal weight. And so to decompose a hat of G, we want to decompose maximal weight. And we have such a maximal weight on G, then the algebra A omega infinity of G is an analytic smash product of two algebras. Algebras, an algebra on B and an algebra of L. And here the weight omega L is maximal on L, but the weight omega B is possibly not maximal on B. And so the first algebra on B is not always an envelope. This is a difficulty, but it's possible to overcome it. And now we want to prove that the smash product of A of B and A of L, after mapping to the above smash product, is homological epimorphism. And we consider the general situation. We have an algebra A and a Hopf algebra H, which acts on A, and so S and K. Of course, to exist such a homomorphism, we need some assumptions on all these algebras. I omitted, and I say only we have a alpha and beta, and alpha and beta are compatible. So the theorem of sufficiency of relative triviality. So we have two homological epimorphism, alpha and beta, with dense ranges. And if the smash product of A and H is relatively homologically trivial, then the smash product of alpha and beta is homological epimorphism. What is relative homological trivial? I said a minute later. I will say a minute later. And so applying this theorem, we see that if the completion homomorphism from AL to A omega L infinity is homological, And if A of G is relatively homological trivial over A of B, then the problem reduced to the case of B. But in fact, we must prove that the map is homological not for Arens-Michael envelope of A of B, but in some different but very similar algebra. So, algebra A is relatively homologically trivial if it is of relative homological dimension 0. So algebra means that we have a homomorphism from R to A, no more. So our assumption is that A is a projective model in the relative category. And this is equivalent that the relative tensor product of A and A over R contains a relative diagonal. Unfortunately, Kerensky cannot hear me, but this is his topic, but for Banach algebras, diagonals. So we need a theorem for a theorem on semi-direct products. If we have a semi-direct product of n and L is linearly couples reductive, then this semi-direct product, A of G, is relatively homological trivial over A of n. And the idea of the proof is compactness, in the same way as the proof of bijet-projectivity of Banach L1 algebras. Because linearly coupled reductions means complexification of a compact Riemann group. And so we can integrate functions. Functions defined on L, we can integrate over K. And the diagonal G is just a function of, that is, an integral over Fk, K to the power minus 1, over, of course, the R measure on appropriate space of Hilbert functions. And so the theorem about about the sufficiency of relative triviality, to prove this theorem, we need also the notion of relative homological epimorphism. So RS, algebra homomorphism from A to B, means that A is R algebra and B is S algebra, and homomorphism from R to A and S to B are commute with a homomorphism from R to S and A to B. And so the conditions are similar to the conditions of simple homological homomorphism. First, that homomorphism from A to B is an epimorphism. And second, that if we apply the projective resolution in the relative category, the factor of the tensor product, when we get an admissible sequence. Admissible in sense of the category, relative category, so splits by morphisms of as by models. And we need the following theorem of Perkowski. So if we have an RS homomorphism from A to B, and so the pair of two homomorphisms, F and G, and if G is a homological epimorphism from R to S, and F homomorphism from A to B is a relative homological epimorphism, and plus two technical conditions, then F is a homological epimorphism. And we need another theorem on relative homological epimorphism. It was proved by Perkowski in the case when B is an envelope, but in fact it also holds in general case. So we need three conditions that G from R to S has dense range and F from A to B satisfies property UDE and also has dense range. And A is relatively quasi-free over R. Of course, all notions need to be defined. And then F is a relative homological epimorphism. So UDE means the property of unique extensions of derivations. So I meet the definition, but if homomorphism is a homological epimorphism, UDE holds. And algebra A is relatively quasi-free if it is of relative homological dimension 1. So before I discuss the case relative homological dimension 0, here dimension is 1. But the name comes from Monaco-Newton definition. I omit explanations. And of course, from being relatively homological trivial follows being relatively quasi-free and also some technical conditions, what we need. And so, in fact, we get reduction. These two theorems, this one and this one, implies the theorem of sufficiency relative triviality. And so what we need to prove that the homomorphism from A of B to the completion A omega B infinity of B is homological. So this is a solvable case. This case is very similar to the case of solvable Lie algebra, so I give only a sketch. Because I recall that omega B can be non-maximal, but it is not arbitrary. It is essential. So every solvable Lie algebra can be represented as a semi-direct sum, iterated semi-direct sum of one-dimensional algebras, Fi. And in this case, universal event algebra is just the algebra of polynomials in one variable. And U of G is a iterated smash product of polynomial algebras. And the decomposition of G can be chosen in such a way that omega B has a compatible decomposition. And then the algebra, the completion of A of B, is in fact an iterated analytical smash product of some algebras, each of which is a certain completion of the polynomial algebra. And this decomposition, iterated smash product decomposition, is compatible with initial decomposition of G. And then we use the result of Perkowski, for an associative algebra of quantum dimension. And if the polynomial algebra acts on R by derivation, then the smash product is relatively quasi-free over R. So we can add 1 to the dimension on each step. So we can apply the theorem on relative homological epimorphism several times and prove that the map from A of B to the completion is homological. This is the end of step 4, is in fact the end of the proof. So I recall steps another times. So first step is a reduction to a Stein group. Second step is a reduction to a linear group. Then reduction to a solvable, simply connected solvable group. And final step is the proof in the case of simply connected solvable group. Well, that is all. That is all. So thank you very much.
Thank you. Questions, please.
Yeah, I have a question. Sorry, I missed the moment when you switched from AG to AB. What was AB? It should be a group there, right? A of G. But close to end, you got B. I'm sorry if I've missed somewhere else.
But what is this light? Yes, G is decomposed into some
Yeah,
direct
you
property.
thought it was AG, yes. And you
Yes.
ended up with
And,
A
and,
of
and,
B.
yes. And then we
You reduced to B.
yes,
Yes.
we have a
You
decomposition.
got the
So
spot.
a hat of G is in fact a omega infinity of G. And this algebra can be decomposed into an analytic smash product.
Okay, so my question was the following. So you got A of G and made it Akbarov's completion, right? Using the submultiplicative seminorms. So is it true that this embedding to Akbarov's completion is always homological epimorphism? Or this may not be true.
No, I'm not sure that it holds, and because
Ah,
I can prove that in some partial cases, this partial case, it is not easy to prove this in partial cases. So in general case,
okay.
I don't know. For example,
So this completion is not Arens-Michael envelope, right? As far as I got. It's something else.
no, it can be an Arens Mach envelope. For example, if G is an abelian group, then G is equal to B. In this case,
Okay, yeah.
algebra is Arens Mach envelope. But in uh, more difficult cases, it is not the envelope. No,
Okay.
it has some universal properties, but another universal properties. And the properties in the sense of Lie group theory, not in the general theory.
Okay.
But
And
fortunately,
final
this is a
question.
very technical proof because well, Lie group theory is not friendly. Just for me.
I see. Well, an AG itself is not a multinomial algebra, right? It has some seminorms, but they are not multiplicative.
A of G?
Yeah, A of G itself. Because it's a
Yes,
strong
A of
dual.
G. Yes, A of G is not arithmetic envelope. So we need
Yeah,
to,
yeah. A of G is not Arens-Michael algebra at all, right? It's something else. It's just separately continuous multiplication there, right? It's really
yes,
bad
yes.
algebra. Okay.
Well, the
But it
multiplication
has
is
some
jointly
seminorms.
continuous, but nevertheless, it is not an Arens-Michael algebra.
Isn't so
It's
extreme,
jointly
right?
continuous, but
Yeah.
if I'm not mistaken, but it is not an Arens-Michael algebra.
Okay.
This is,
But it's nuclear. But it's nuclear,
let, let,
right?
just wait a minute, where show. As this case, simplest case, A of C, one-dimensional algebra,
Yes.
via Fourier transform is the
Yes,
algebra on
yes.
functions. A functions, Golomorphic function of exponential type is not arithmetical algebra, but nevertheless has a jointly continuous multiplication. Yes.
Okay, okay. Yes. Okay. Okay. Yeah. Thanks. Yeah. Thank you.
More questions, please. Well, it would be interesting to look at the not at the complex analytic, but now at the real case. So, I mean, the algebras of distributions on real Lie groups. But in this case, we, I suppose we don't know anything already in the case where we take, for example, the real line. So, what is the Arens-Michael envelope of the algebra of compactly supported distributions on the real line? I
Yeah.
don't know.
Yeah, no, yeah, I think if we use Fourier transform, uh,
Hmm.
we get some algebra, no, preliminary
Hmm. Mhm.
several also. So I think that in fact it will be the algebra of infinity functions on the real line, maybe.
Well,
But how to generalize it to general case, I don't know, because no, Arens Mark envelope is good for analytic functions, but not differentiable functions.
mhm. Okay, are there any other questions?
By the way, do we have sort of sheaf extension here in this theory? A sort of geometry. Starting from the group by somehow get sheaves somewhere.
Oh, it shifts on the spectrum.
Yeah, so it
No,
would be nice to have sort of,
we know that even for in the nilpotent case, there are some problems with shapes. Yes, so we need to
yes.
modify the algebra to get some shape. And, yes, maybe
But
the envelope with respect to the class of PI Banach algebras, Banach PI algebras,
oh
then
yes,
we
yeah, yeah, yeah.
have some fifth. So,
Yeah, I know, yeah.
so there are questions which
More than
which
solutions.
deserve some consideration. Yes.
Okay, okay, thank you.
More questions, please. Well, if there are no more questions, then we thank the speaker again. Thank you very much.
Bye.
And well, see you next Friday.
Спасибо.
Спасибо.
До свидания. Bye.
До свидания.